So I think Mihao mentioned that he fixed something. And I think now we can get it to work as long as I do git. So git check out. Is this the way it works? Okay, so he did actually change something in Maxcad solver. So let me see if I can now go to, so I was reading these, then I keep forgetting how to get there. How to get the repo, yellow submarine code, research paper code. Let's see. Let's see. So many commits. I'm just curious what he changed 3 days ago. Oh no, I did it to readme. Okay, so the links and stuff, cool. That's good. Fix typo. Ah, you see. Okay, cool. So this is the regularizer. Okay. So that is what was happening. That was the problem. Okay, cool. Happy. Thanks, Mihao, for doing that. Now let's see if we can get it to run first, and then see if we can, like, where can we move from there. But has this been updated? So what is the? Why hasn't this updated? Man, I don't know about. I forgot even how to use Git. That's so sad. But that's what he changed basically. So Git checkout, right? Oh, Git pull. Yeah. Congratulations. Git pull. Git stash. Yeah. Git pull. So I'm getting basically, okay, now I'm getting the last version, which has the fix. Yay, cool, perfect. And now I'm gonna try to basically get it to work. And if I remember well, which I don't, how to run that, how to run that. It was basically, see what happens. It's been a while since I touch it, and I tend to forget quickly. So basically Python. Okay, so basically like just running it with Python. So maybe if I do that. Python. Was it the example that I have to run? Example. So where am I right now, first of all? Okay, so Python yellow submarine example PI. See what happens. It's thinking. It's thinking. Warning. Dun, 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 dun. Hopefully it doesn't break anymore. Hopefully there's no problem with the dependencies, instructions for updating. Oh. Wait a second. What is all that? Graph options, keep checkpoint. Maybe that's coming from. TensorFlow stuff. What is it? What is it going on here? It's those seem to be warnings. Using default stuff. Blah 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 blah. Okay, but Is it still going to run or what? Create checkpoint, save a hook. I don't know what's going on. It seems it's still going, trying to do something because of the TensorFlow dependency problems that I had. Graph was finalized. Okay. Whoa. It's just too much output at the same time. I don't know what's going on here. So I still, while this is running, I still didn't really get the gist of QAOA, in the sense that, I mean, at the end of the day, it seems to me like most of the stuff is just easy in the sense of it's just the same concept, like you just parameterize something and then, you know, play with different parameters and try to optimize sort of the cost function and then change the parameters until you find something that's your minimum. But what I'm not getting in this case is how do you build that? So how do you build the circuit? That's so slow because of the VM, I guess. Sorry for that. Okay, it's still doing stuff. So maybe because of the QAOA. So this kind of seems to create a circuit, right? If I remember well, like a parameterized circuit. But then still, how is that generated at all? Like, is it like a general recipe? Because I think I should just, next step is just Google QAOA, like maybe outside the context of the project. So QAOA explained. Okay, so there's a paper. Then there's some videos. Then there's an introduction. Okay, maybe that would be a good one. Okay, so there's a paper, which is 19 pages long, and this is 16 pages long. It's an introduction. Problem statement. Discussion about whatever. Discussion about whatever. Rotations, workflow. Maybe, okay, maybe that's a good one to read. Although, actually, I remember that they did a paper also for this project, but I don't know if that paper is approaching graph balance with continuous variable. Okay, now that's more like the CV approach, but it's still like, okay, I think I'm gonna go through that now. But maybe I'll do that out of the. I think I'll do that out of the virtual machine because. Oh, that's fine. I'm here now. I mean, let's see. Did this run? Yeah, cool. It ran. Okay. Total cost. Can I compare those results with this? Is there somewhere where I can see the results? No, that's not. That's I want the project code. I want the project code. Okay, but here there are no results. Okay, but basically total cost is whatever, and then this, like, I think the zeros are in this case what? No. What am I doing? Research, paper, code. Because in the paper, maybe they talk about the results. Do they talk about what's the example results? I kind of think I remember seeing those example results. Maybe this is here. Introduction. This is the problem exactly, and here. Okay, but this was a. So this was a graph. Okay, let's see if I can actually. Let's see if we can do that with this graph. Because here's a bit of a different beast. First graph. Like, if I change the example, yeah, but the parameters are different as well. I don't know if this is the graph. I want to, yeah. 4 nodes. Interferometer, use for the circuit, the array. Ooh. Example. Training parameters, gate structure. Gate structure. Yeah, but I don't know what's the graph that we're trying to solve here. Is it A? Is it this? Doesn't make sense either. I mean, I don't know. That's the adjacency matrix. I'll have to figure it out. I've got solver. Okay. Anyway, I'll. So it kind of it runs, but I wanted to check whether that will work for. So I wanted to check whether that will work for that example as well, but I don't know. I don't know how to do that. First graph, Max got QAOA. Topo measurements, qubits. I don't know. Maybe in the paper. Maybe in the paper there's the definition. Circuit design. Okay, so here's something. Create a distance matrix A of the given graph. Okay, so that's how the graph is represented with a distance matrix. Rescale the matrix so all the eigenvalues are between 1 and -1, excluding these values. After this procedure, we get a matrix A. Okay, so that's what it's doing. So the matrix A is what it's the distance matrix. Yeah, but in the example, okay, so that's, I assume, the 0, 1, 2, 3, 0, 1, 2, 3, right? CCC is basically constant. So the values of A are in the range. It seems to me there is something in here like this, like there's work that's not in the code, right? Which is the C's have been chosen, and the C's and the D's have been chosen so that the eigenvalues of A are in the range of 1 and -1. So if I change that example, those numbers probably won't work. So that example probably won't work either. So that kind of Okay, and then the interferometer matrix, I don't know if that's helpful. What is it for? Okay. But it seems like it's running. And then those are the solutions, and I think then in this case the top ones would be the ones that we want, right? So this one and this one, this kind of splits. Okay, so let's go back to the QAOA thing, the introduction. So let's see what's the thing here and how, because it seems to me that doesn't necessarily have to do with continuous variable quantum computing. It's just you can do that with CV quantum computing, but also with DC quantum computing. I'm curious about what's the concept behind QAOA. QA, is it the same thing? Quantum approximate optimization algorithm. The quantum optimization approximation algorithm. I think that's because the name is a little bit different, but I think that's it. QAOA, yeah, QAOA. So maybe the first pages would be kind of enough. Quantum is one of the algorithms that can be implemented in near-term quantum computer. It's one of the most promising algorithms in history of quantum supremacy. It's an approximation algorithm, which means it does not deliver the best result, but only the good enough result, which is characterized with a lower bound of the approximation range. Okay. Works in some explicit. Okay. The report is organized from first I have a recent development in the method, then we gave the extensive explanation of QANA. Okay, so development for QANA is 2014, so it's fairly new. I was applied to the max-cut problem initially already. Okay. No, not interested in that. Not interested in that. Not interested in that. No. Let's skip. Problem statement. Some of the explanation might be trivial to readers, but they are important for beginners to understand the reasoning. Thank you behind it. For such details, they will be moved to the supplementary part of the to make the report concise. Okay. Suppose we wish to maximize an objective function. Z is a substring system property. I'm just scanning through. I'm really not fully understanding everything as of yet. Right now, there are it's still unclear how to solve the problem. If an approximate solution is all we need, then we're already many classical. However, we probably can do better using quantum approximate optimization algorithm. The first step is to treat the objective function as an operator. Okay. The C has eigenvectors. Man, that's dense. Expectation value. Find a state. So finding Z that can maximize CZ corresponding to finding a state is to maximize C. So, okay, so it seems like the idea here is that whatever you want to optimize, that cost function is turned into, okay, so it's a transformation. So it's kind of a gate, or like a set of gates that you want to use, that you apply to your state. And then you want to, okay. You obtain the probability one. But in general, we don't know how to find size C max efficiently. We can only find C that is close to C max. Can we find that is a superposition of probability for obtaining Z, hoping that it's large enough so that we measure. Yeah, and so the idea, okay, so the idea here is you construct, so you're kind of constructing your function within the circuit, and then you just shoot it a superposition, hoping that the result will then be visible the best result will then be visible because of the amplitude will be bigger. So it's just okay, kind of the typical process of just shoot it to superposition. Okay, but the trick is in how to build this C, right? So that's kind of problem. So I'm smelling this is going to be some kind of generic set of gates that are parameterized, and then you just play with the parameters. Yeah. Probabilities. Oh my God, this is so dense. I think I'm skipping the maths and go. Oh, good. I'm going to the circuits. Or discussion about this. First, we discuss operation U. See this, which is defined as this. T means charted decomposition and is an angle, which will come back later if two are commuted. Oh. This is quite dense. Successively. This means some component Z phase will be added in front of Z for each of the satisfied condition. Okay. So they are playing with phase flagging, or what? Okay, so it seems like this is you're shooting something that's supposed to phase the right solutions to add a phase, so you can then identify the circuit will be. Okay, in that angle, so the way you phase it is still important, maybe. For a component, just table, the truth table, whatever. I'm really scanning that. I'm really scanning that. I feel like I can construct a circuit with the help of ancilla qubit 1. Okay. Yeah. So when this is 1, then there's a rotation happening here based on this angle. Okay, so this is maybe then the angles we're talking about. C maybe being those constraints, right? So I think the idea is maybe here that you want a certain constraint. So you want constraints within the input to be correct. So you want to filter the ones which are not correct. So this is a basic kind of multi-control circuit. And then you kind of add a phase. You add a phase to those states that are correct. Okay. Intuitively okay. Discussion of UB beta. Okay, so here are those angles that appear in the project as well. Phase change. Yeah, of course, the phase doesn't change the probability of obtaining a certain result. So what does these do? We don't know. Depth 1. Those are rotations. Okay. So what this does is it rotates around the x-axis, which means it rotates between zeros and ones, right? Like that would really manipulate the probability of measuring something, of measuring 0 or 1. Workflow. It is not guaranteed that after. Okay, so it seems it's 2 steps. Like you get your input, then you're phasing something, and then you're adding a certain phase, and then you're adding a certain rotation. So there's no guarantee that's good enough or close enough to Z prima. I'm not sure if he's applying it multiple times with different Yeah, so the natural remedy is just play with the angles. Why? So then we have a new state that depends on the angles. Here's a typical workflow. Begin with a trial state. Okay, I like the workflows. Classical computer initialize parameters, beta, and whatever. Quantum computer, construct this. Okay, with angles determined in previous step. The circuit for individual operators is shown in the previous sections. Now, news updated. Quantum computer measure in computational basis Z and obtain a value Z. Then use this Z to calculate the function. Then repeat steps 1 to 4 to a number of times. It means we measure the same for many times and to obtain distribution of states Z. Yeah. Each Z corresponds to a CZ, which results in a distribution of CZs with largest values. Yeah. Select a new set of parameters. Repeat 3 to 6. Obtain a distribution and then choose the largest one. The termination condition depends on how you update next set of angles. Okay. So I think I understand the general idea. I mean, it's not so sure. I'm not so sure why this circuit works. I haven't really, but maybe let's go through the actual maxcut example. Here there is applying maxcut. It's interesting to see how different objective functions C apply to Q. Okay, so C is the objective function. The problem can be phrased this way. Suppose we have a connected graph, it can be determined by n vertices, blah, 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 blah. We can classify each vertex into one of the two categories by setting values +1 or -1. A cut occurs if two vertices of an edge disagree. Our goal is to find a construction such that we have the maximum number of cuts or disagreements on the edges. Notice the true maximum could be less than m. Consider cutting a triangular as an example. So our objective function becomes, okay, yeah. Okay. So this can be translated in the following. Consider n vertices as n qubits. By the way, I still don't see how VC, like I don't know how CV quantum computing plays into this, because this seems like something that can be solved with discrete quantum computing. It's just rotation so far. If edge is a cut, then see how this is implemented. Can we see how this is implemented? Okay. Can be verified that. JK. So why is this circuit working? So I'm trying to figure out why is this all working. So basically, translating the problem like that. But what is the state? Oh, this is supposed to calculate the, okay. But why is the rotation here? How is the rotation here meaningful? Oh, the rotation is because Mm. Okay, so this I'm gonna come back to this, but so this is circuit. Okay. Pretty darkly. As a result, we can implement it using C-NOT gates, and the second part is a phase change, which can be done using this. Circuit with, whoa. Sorry. What have I done? As can be seen, a phase is added to Z. Okay, so as you can see, a phase is added to Z if two qubits are different. So a cat. XJ, XK. What is two qubits are different? So how is the problem encoded? Okay. So the qubits are the not the links between, but they are like the edges, not the edges, the nodes of the graph. Correct? No, at the edges. Okay. So okay. So maybe XJ is okay. That's one register, and that's another register. Okay. Yeah. Probably that's what makes sense. So it's defining sort of the category of each of the. Really? I don't know. But conceptually, it says it's adding a phase to Z if the two qubits are different. So there is a cat, which is exactly what we want. Which is exactly what we want. The operator is the same as the normal workflow will be the same as going to structure. However, some can be performed based on the property of the graphs. Subgraph that is p steps away from this graph stuff. This is a condition indeed only in final project. Okay. So consider. So that's an example. Okay. So this is kind of what you're applying. So these would be the qubits. Okay, so it's kind of doing that. I think what I will try to do is I'll try to build that actually in Quirk, but I'll do that in the next video. Okay, so QAOA and Quirk, that's going to be the next video. Because I'm definitely not going to go through all that stuff. Okay, but I'll save this and I'll try to build that circuit and understand why it works. That makes sense. It's easier than go through the maths. Okay, nice, perfect. Cool. So that's a little bit better, but still I don't get how that does this feed into the continuous variable quantum computing thing, because that's something you can solve with discrete quantum computing. Perfect.